thank you very much, first of all, for the invitation to the organizer. It's beautiful to be here. So I was asked to prepare a mini course, so I thought to do this about the Bernoulli free boundary problem, which I'm going to state soon. It's a nice place to do that because I also explain why some years ago I got interested in this problem, and it's due to some people in this room, so why not? So in particular, it means that there are experts in the room on this free boundary problem, but I'm planning to do the class somehow an elementary class, so I think that several people might be bored, but I hope that some other would grasp some idea. So everything I'm going to do is quite classical, so I'm not really getting to the new things probably, but at least I think I'll try to convey some classical ideas that are still used in the research as of now. So, okay, so what's the Bernoulli free boundary problem? Well, the Bernoulli free boundary problem, which to my knowledge was, but probably is not the case, was first introduced, or at least the first paper, no, definitely was not, but the first paper in which he studied in the way that I'm going to describe is a paper of Alte Caffarelli in the 80s. Is the following variational problem. So actually is slightly different variational problem, but I'm going to focus on one, but maybe let me write more than one. So given a function u, say from a domain, so you can also fix some notation, u goes from a domain over D into R, we can define the energy of u for omega. Okay, so it's given u, let's take also possibly three constants. Lambda 0, lambda minus, lambda plus, and I define the energy of u omega as follows. So it's the integral of the gradient of u square over omega, so the classical Dirichlet energy of u, and then I add the measure where u is positive, lambda plus the measure where u is positive, plus lambda minus the measure where u is negative, plus lambda 0 the measure where u is 0. Okay? Inside omega, everything. So here I always have to intersect with omega, intersect with, right, at least the first formula, let me write it correctly, intersected with omega, intersected with omega, plus lambda 0 is 0, intersected with omega. Okay, so essentially, so two remarks, one more useful, one less. So the less useful remark is that you see the sum of these three terms is the measure of omega, which we can assume to be, let's assume it's finite. So essentially, you can always remove one of the three. But still, if you write this way, you see that, you really care about three different phases, in a sense. So I think this is a more symmetric way to write it down. And then the next thing to look at is, so what would so I'm going to consider this, so actually, let's call it two-phase problem, Bernoulli problem, is, if you want, the study of minimizers, or local minimizer if you want. Minimizer of J of u omega. Okay, so which is like functions such that the energy of U in omega is less or equal than the energy of E in omega for any other V such that, say, the support of U different from V, I mean, let's say the set U different from V is compactly contained in omega, or something like that. Okay? Or you prescribe some boundary value. I mean, this everything I'm going to do is a sort of local thing. So, okay. So the study of this of minimizer, and in particular, I'm trying to ask to answer to 3 questions. The first one would be existence. The second one would be regularity. And regularity is actually going to split into regularity of minimizers, and regularity of the free boundary. So, and let me start immediately by singling out one particular case of this problem. So maybe, okay, since it's the one I'm going to study, let me slightly change the notation here so that I can save the G letter for later on. So let's take G tilde. Here. And so let us assume that lambda 0 is equal to lambda minus is equal to 0, and that there exists G from the boundary of omega into R is non-negative, then I can define the energy, again, Ju of omega, to be still Dirichlet energy, and this time I mean, it's the same energy, but I'm only seeing these 3 constants are positive, I mean, like, okay, distance. So that's it, non-negative. So I'm taking 2 of the 3 0, and I look to this energy, and I look to minimizers, say, of the same energy, which are equal to G, V equal to G of JV of omega. Okay? So I'm looking to the energy, I'm prescribing a boundary data, and the point is that the boundary data is non-negative. Now, because of this, it's easy to see, so the remark is that with this J of the positive part in omega of U, so let me put the positive part below. So for me, U plus, I mean, for any function is going to always be the max between U and 0, so it's the positive part. So the energy of the positive part is less or equal than the energy of U. That's true for any U, essentially. That's, in this case, for this J. This wouldn't be true for J tilde. That's because this term is the same, and this term only decreases, right? So there is no point for a function to be negative if you look to that minimization problem, okay? So actually, there is, so that's, so that one is the two-phase Bernoulli problem, but this one suggests that a simpler situation will be to study, what is the one-phase Bernoulli problem, which is the study of local non-negative minimizers of, okay? So, and this is the problem I'm gonna concentrate most because it's somehow easier than the other. So then if time allows, I can say something also for the other problem, but I'm gonna focus on this problem. Okay, so these are the problems I like to study, so maybe let me spend a few, I can't use two at the same time, right? Maybe let me spend a few words on the motivations, and okay, there are several motivations to look to this problem. One, I think, the main one is that it's beautiful. But the reason I got interested, like people in this room, which is Doreen and Jimmy, they made me interested in this problem, is that because it's related to shape optimization problems, okay? So, and so let me give you, so actually, as the name Bernoulli suggests, this problem, was introduced to study certain configuration of for stationary flows, so in channels and so on. So it starts from fluid dynamics, which is not where I want to go, but I'm more interested into this like shape optimization problem. And actually, let me also give you maybe another problem which we have seen somehow partially, at least in these talks, which is well related to this Bernoulli problem, which is the problem of capillary surface, so the capillarity. So if you want to show what is the shape of a drop lying on a substrate, essentially, I think this goes back to Gauss, what you expect is that the optimal shape would be a minimizer, so the optimal shape should be a minimizer of a function of the following type. So you should look, so let's say if this is a set, for any set, which is say lying, for instance, in the positive Hall space, so you can imagine that this is modeling like a drop on a table. What you expect, it's a phenomenological energy, so was suggested, I think, actually by Gauss himself, that the energy that counts should be, the area should be proportional to the surface tension inside. So let's say the area of the boundary of the set inside the Hall space. But what they observe is that these drops, they hit the table with a fixed angle, which is capillarity angle, which depends on basically the material of the table and of the liquid in the drop. And while minimizer of this energy, so they will always hit the table with 90-degree angle. So what was suggested is that it should be added a term of the form sigma times the measure of the boundary of E into the boundary of the surface. So essentially the energy is the sum, we have shocks. It's the sum of two terms. One is this one. Okay, it doesn't look very different from which comes from here. and one is this one, which comes from here. And most likely, if you do this minimization problem, you're adding here some constraints. Usually it's a volume constraint. Now, this is a very well-studied problem. And what one expects by this condition is that minimizers, so one expects minimizer satisfy the Euler-Lagrange equation. So when you essentially do variation inside, you expect that the mean curvature of the surface to be either 0 if there is no volume constraint, or maybe the Lagrange, let's make it constant, the Lagrange multiplier of the constraint, and then there is an interaction between these two terms, which is really what is giving you the angle here. So you expect that when the boundary of the set gets to the table, so this angle here, let's see, I mean, which is basically the angle, okay, I always, so let's see if I get it right. So it should be this angle, I mean, this angle here is the same as this angle here. So the angle between the normal of this, imagine everything is smooth, the angle between the normal to the surface and the normal to the table. So maybe let's call this nu boundary of E, and this is nu of the boundary of H plus. So what you expect, E dot the nu of the boundary of H plus to be sigma, I mean, let's say plus or minus sigma in the sense that I never remember in this configuration which is the sign, but you can try to guess. So essentially you're meeting with a prescribed angle, okay? So this is actually what you observe for capillarity droplets, and this is what led to this model, and so the study of this model. Now what's the link? Well, imagine that you're in a situation in which you can write, if the boundary of E is the graph of a function u, at least locally, so what would be the energy here around? Well, the energy, the capillarity energy, would be the integral of the area of the graph, right, plus sigma, the measure of the wetted part, right, which is the set where u is larger than 0. So you now see that this function looks pretty much like that, except in particular, you might expect that in the regime in which one might expect that in the regime in which sigma is equal to epsilon k, say lambda, if epsilon k goes to 0, then uk, so if you take uk to be the minimizer of something like this, with this sigma k, uk over epsilon k goes, okay, maybe it's not, I think it's epsilon k, it's still, there are biteric function, goes to the function v, which is a minimizer. So you see v, so if you imagine that uk is like epsilon k times v, you see here you get a term which is infinitesimal, so you might expand to the, you can Taylor expand. So you expect to see v, a minimizer of gradient of v square plus lambda measure where B is positive. Okay? Yes? Bigger? I'll try. Okay. So, I mean, I know I always say I try, but then I converge back to the... So, I mean, there is a relaxation time, which I think it's quite short. Let's see. Okay, so you see that there should be some nice connection between minimizer of a capillarity problem and minimizer of Alt-Caffarelli. So this is formal at the moment, but actually it has been formalized by Chodos, Edelen, and Lee, and recently has been used to move results from the geometric problem to the Alt-Caffarelli problem and vice versa. I mean, in a sort of back and forth way, which is very interesting. Okay, but that was one motivation, and the other motivation, as I was saying before, is about shape optimization. So let me maybe mention. Can I erase here? Okay, maybe let me use this blackboard. This one. But that's the Swiss. The German style, yeah. So Anna, she was very, see that she's working. So let me maybe just mention quickly the shape optimization side. So this is essentially about looking for optimal sets which minimize functionals which might depend on the set in some non-local way, mostly by solving some PD on the set or on the complement of the set or something like that. And they appear in a lot of applications. So one, for instance, is about constructing an optimal capacitor. So if given a set, so say that you have a set D, which is a subset of some omega, and then you can define the capacity of D inside omega as the infimum of the Dirichlet energy of all function u, such that u is equal to 1 on D, and u is equal to 0 on the boundary of omega. So the picture will be that this is your omega, this is a set D inside, and you look for a function u, which is essentially making the optimal transition from 1 to 0 on that set. And this is indeed, I mean, if you think D as a capacitor, this is actually the capacity, the electrostatic capacity, up to constant here and there. And the natural optimization problem would be to find the optimal, I mean, given omega, the optimal D for the capacity. Now, if you do this, you see, I mean, that essentially you can make the capacity extremely small by taking sets which are smaller and smaller. So you would like to put some constraint on D, and the reasonable constraint would be to minimize the capacity D in omega when you fix the measure of D, and it's prescribed, which then is almost equivalent. I mean, here it's a big. I mean, this is not true actually, and it has been studied when it is true and when it is not, but just let us assume it for the sake of the talk, to minimize with a Lagrange multiplier. Okay? So you see that this problem, I mean, you don't want to have, I mean, it might not be convenient to have measured 0, right? Because positive measure will still drop in the, so this times it's a free minimization problem. So let us assume that this is an equivalence, which is not. But in any case, you can just study this problem. And if you study that problem, so you see the capacity is itself a minimization problem, right? So you have a mean-mean problem. You can make it a only unique mean problem. So essentially, this problem here is equivalent, let this go star, to minimize the Dirichlet energy of V square minus what will be D. Well, if you look to that, say U, if you look to the definition of capacity, D is the measure where V is equal to 1, right? So, and this will be among all function V, which are, say, in H1, 0 of omega. So, where this is the set of function which vanishes on the boundary of omega, okay? But now, if you define U to be 1 minus V, yes, so this is the same that minimizing the energy of U square minus lambda times the measure where U is equal to 0. But now the measure where U is equal to 0 is the measure of omega minus the measure where U is positive. So this is equal to the minimization of the integral of the U square plus lambda, the measure where U is equal to 0, minus lambda times the measure of omega. Okay? So this is just a constant. So you are really looking to a Bernoulli free boundary problem. So one-phase Bernoulli free boundary problem. It's easy to see that for this minimization, there is no reason for the function to be above 1 anywhere. So for this one, it means that U, there is no reason for it to be negative anywhere. So, okay. So, and if you want, you're minimizing this among all function U, which are in 1 plus H1, 0. So they are 1 at the boundary. Huh? Yeah, the gradient squares. Okay, so this is a situation in which you end up really on the actual Bernoulli free boundary problem. There is another one I want to mention because here I think here it has to be mentioned, which is sort of a which. Which is the following. So again, given a set omega, we can define lambda of omega to be the first Dirichlet eigenvalue of omega. It's already appeared in the talk of Doreen, which not by chance, which is the smallest positive number, such that the problem minus Laplacian u equal lambda u in omega and u equals 0 on the boundary of omega as a non-trivial solution. And now, if you start from this, it's well known that lambda omega can be characterized as the minimum among all function in H10 of omega, except the null function, of the Rayleigh quotient. And now, given, okay, so this is the characterization of the first eigenvalue, and now you can wonder, a typical shape optimization problem is like the easiest shape optimization problem is to minimize lambda of omega, say among all sets contain maybe, okay, omega is usually my box, but let's say then in some larger set U with possibly some fixed volume. Again, there is some monotonicity of this guy by inclusion, a reverse monotonicity. The bigger is the set, the smaller is the eigenvalue, so you should make it, should put some constraints to make the problem interesting, which again, and Jimmy hopefully would forgive me for that, because it's not the case. This is it's not. But sometimes it's equivalent to minimize the eigenvalue minus, okay, maybe there's an unfair choices of parameter. Let's maybe call it A, the plus this time. A, the volume of omega. So this would be the Lagrange multiplier version. And now you can imagine, okay, you know that, I mean, this is zero homogeneous, so you can sort of assume that U square is 1. So you can sort of imagine that the eigenvalue is almost like the integral of du square, and that the other terms it counts less. But what would be then omega would be, for instance, the measure, well, it's the measure where the first eigenfunction is positive. So you see that up to some higher order term, you are really minimizing a Bernoulli free boundary. So if you care about the behavior of minimizer of the first eigenvalue, or things which looks like the first eigenvalue, you actually care to, I mean, before understanding that one, at least you like to understand what happens for minimizer of the Bernoulli problem, okay? And maybe here there is another important fact on which I'll insist more and more, which actually says, if you look to the problem, to the geometric problem, like minimizing the capacitor, minimizing the eigenvalue, what you really care is not too much about the function, but is more about the shape and the behavior of the set where U is positive. And in particular, you always care, so let me maybe put this remark, let me put it here. So remark. So in shape optimization problem, we care about the set U positive and its boundary. It's the boundary. So we would like to understand properties of this set, and in particular, since the set is defined by its boundary, of, I mean, it's boring, the set outside the boundary, of this one, which is what is called the free boundary of the problem. Okay. So this would be the main focus of, I mean, the final goal, let's say. It's not just the main focus. So I'll try to convince you that, I mean, if you want to understand this set, it's better first you understand U, and then you go to that set. So still we have to understand what is happening for you, but the main goal, the final goal will be to understand this set. Okay? what we can say about that set. In particular, maybe just a trivial observation is whether that set exists. I mean, is there always a free boundary? I mean, can you show? And why do you expect the existence of a free boundary? So maybe let's move then to the study of the problem. So this one maybe I don't need. Okay. So when I speak about regularity, yes, I care about the regularity of the function, but I also care about the regularity of the free boundary. I care more about the regularity of the free boundary than regularity of the boundary, of the regularity of the function. But okay, so no. I can't move one up and the other down at the same time, right? That would save time. So this one is my problem, so I'll put it up there. And this one, this one. Thanks. Okay. Great. Okay, so let's move to study this problem. I hope in this first part I convinced you about the interest in studying it. So now you have a variational problem, which again is that one up there. So the first question, let's call it zero question, is about existence. Okay? If you don't have minimizers, the problem is already. I mean, it might be interesting, but let's start to have something to study. That's a good starting point. And existence is just a direct application of the direct method of the calculus variation. So this comes from the direct method of the calculus variation. And there is not too much to study. Just maybe a remark. So you take a minimizing sequence. The energy are uniformly bounded. If you are prescribing some boundary data, this implies that up to subsequence, UK converges weakly in H1 to some U, and UK converges to U almost everywhere. I mean, you can assume that. And now it's immediate to see, I mean, that's just a lower semi-continuity of the Dirichlet energy. It's well known. So what happens for the other term? Actually, since you have pointwise convergence, what you get is that the characteristic where U is positive is less or equal than the lim-inf as k goes to infinity of the characteristic where UK is positive. Okay. So this implies that by Fatou lemma, also this term here is lower semi-continuous. So for the one phase, so the only reason I'm showing this this proof is that just to remark that for the one phase this is immediate. For the two phase, so with the three coefficients, this applies to the positive and negative part. But then the zero part is the other one, right? The sum is, I mean, the sum is constant. So if two are lower semi-continuous, the third one has to be upper semi-continuous. So their existence depends on how you choose the lambda plus, lambda minus, and lambda zero. So there should be a relation, right? Essentially, it should be, I mean, you can create zero out of nowhere, and you should have a relation saying that this decreases the energy. Okay, that's just a remark. Okay, so lambda zero should be less than lambda plus and lambda minus to hope for existence. And actually, in a sense, this is an important condition for several other things. But okay, so existence is easy. Maybe a quick remark. Put it here. The functional is not convex. It's not convex in U. So in general, we do not expect uniqueness. And also, in a sense, we expect that, we expect that being just stationary, first of all, we expect not to be clear what it means to be stationary. Second, we expect that stationary points are not minimizers, so minimizer might behave differently from stationary point, and then you can have all of a sort of zoo of behavior, okay? So that's for non-convex minimization problem. Usually stationarity and minimalities are not the same, and even stationarity might not be completely well defined. And maybe I'm gonna discuss this now. What does it mean? But I'm gonna study minimizer, so this is somehow should be the strongest possible notion, okay? I used to say that not everything that I'm going to say for minimizer applies then for a stationary point or things like that. Okay. Okay, so existence is fine. Let's move to indeed Euler-Lagrange equation. Both formal and non-formal. So let me take this function on a bit. No, where is the function? Here. So we have the function, yes. Okay. Okay, Euler-Lagrange equations. So you see, we would like to, any critical point, any minimizer should be a critical point for variation. Now, the point is that I'm going to show you that there are, it's not completely easy to understand how the functional behaves under variation, because definitely, the Dirichlet energy, we all know it behaves, but the measure where U is positive, it's somehow non-local. To move it, to change it, to say something about the term you would like to change, the measure where U is positive, and this is not completely easy to be done, or to understand how it's done, by the usual, say, vertical variation, right? What we are used to do in variational problems is take U, add to U epsilon phi for some test function phi, expand the energy in epsilon, and say that the first order term should be 0. Now, you can do that. Definitely, this is going to be true, but in a sense, the functional is not really going to be differentiable in epsilon, and that part there, it's not completely easy to understand how it behaves, right? On the other hand, at least you can do something in which, let's say what happens if you take variations, then do not touch the set where u is positive, right? So if we take phi such that phi is C1, compactly supported in the set where u is positive, then for epsilon small, the measure where u plus epsilon phi is positive is really equal to the measure where u is positive, right? Which then say that minimality implies that the Dirichlet energy of u square is less or equal than the Dirichlet energy of u plus d phi square, which is, shouldn't say. Now this is the classical computation. This is epsilon, maybe there is a 2, du d phi, epsilon square. And this implies that du dot d phi is 0 for any such phi, which implies that Laplacian of u is equal to 0 on the set where u is positive. Now there is a caveat. What's the caveat? It's not open. Yeah. So this set a priori might not be open. So you indeed expect u to be harmonic, where it's non-zero, but still you need some regularity to say this. Okay? But even if you assume it to be open, so that say u is continuous, so this is implied, that's not equivalent, but this is implied by u continuous. Even if you expect that, you see this is it's an information, but it's only an information about u. I mean, I haven't moved in any way this set. I haven't changed it, in a sense. So it's definitely missing something. I mean, this can't be all the story, because I'm only using half of the function. Okay? Okay, but so that's the first half of information. There is, so this is not yet rigorous, but there is something we can do rigorously, so at least get half of the thing, which is the following. So maybe I'm going to do it here. We can still do some meaningful deformation for which we understand a term like this. So now let's take u, my minimizer, and then take a v which is less or equal than u. Okay? Now if v is, so u would be something like this, and v is below u. Okay? Now if v is below u, also v plus is below u. Remember, u was non-negative. Okay? And now this means that if v is positive, u is positive as well, right? I mean, in my picture, that's this. So what would be v plus? So this was u, this was v, and this is v plus, which means that the measure where v plus is positive is less or equal than the measure where u is positive, right? Now this means that the fact that the energy of u in omega is less or equal than the energy of v plus in omega, which implies, I mean, since this term actually is less for omega, for sure for u it has to be less the Dirichlet energy part, right? So this implies that the integral of du square is less than the integral of dv plus square, which is less than the integral of dv square, right? So u minimizes the Dirichlet energy with respect to any function which is below u, right? And this is saying that u is subharmonic, okay? Possible definition of u subharmonic. So this implies that u is subharmonic. Yeah, okay, I would take this as a definition, but you can also say that the integral of du d phi with the minus is larger or equal than 0 for all phi which are non-negatively smooth and compactly supported in omega. Okay? Yes, for instance, a definition of being subharmonic. These are equivalent because the Dirichlet energy is indeed convex. Okay, so at least we have some information which is actually true and global, which is that U is subharmonic. This one yet we don't know, so I'll come back to this. But let's see that again, at least if we, okay, so this one I'll keep. This one I'll keep. So let's see if at least we can say something formal for you. And again, as I was saying, to say something meaningful, we need to move the free boundary. Because, I mean, the set where U is positive. Otherwise, there is. If you don't touch it, it doesn't give you any information. Okay, let's go faster with this then. So to do that, we are now gonna do what is called an inner variation. So let's see if I do this computation correct. So we do what are called inner variations. And okay. So what we take is the vector field X. So this is infinite. Well, C1 is enough. Compactly supported in omega with values inner D. So this is a vector field. And we construct phi epsilon of X to be X plus epsilon chi of X, right? So essentially what we are doing is that we are moving, so any point inside X by this vector, epsilon times this vector field. Okay, so it's easy to see that phi of epsilon, because this is compactly supported, I mean goes from omega to omega, is a diffeomorphism. And what else? And it's the identity on the boundary of omega, right? So this guy is 0 on the boundary of omega, so nothing is moved there. And this is true if epsilon is small. Okay? This is compactly supported. You take epsilon. You can check this. Now we consider, so U is my minimizer, and then I consider U epsilon to be U composed, I mean, I think it's convenient to say with phi epsilon to the minus 1. I think it's more convenient. And, okay, this is now a good competitor. Okay? So, and now I know that J of U in omega is less or equal than J of U epsilon in omega. And I like to see what this is. Okay? So what would be J of U epsilon is the integral of the Dirichlet part, which is, let's see if I do this correctly, it's d phi epsilon. So it's d of phi epsilon to the minus 1, I think transposed, times d of U in the point phi epsilon to the minus 1 of X square plus the measure of, see if I do correctly, the set where phi epsilon positive, right? Because if yes, no? If this is, if x is where this is positive, then phi of x is where u is positive. I think that's correct. So now I have to massage this part. So this guy here, so that continues here, is, now I can do a change of variable here and call this guy y, right? So x is phi epsilon of y. That's the reason why I was starting like this. And what I get is so what I get is d phi minus 1 epsilon transposed computes in the point phi epsilon of y times du in the point y squared plus, and then I have the determinant sin. And then I still, so I'm integrating these things, y. And here, again, by change of variable, I get lambda, the integral where u is positive of the same, the determinant. Okay. And obviously, this integral is the same that integrating where u is positive, right? Because otherwise the gradient. So, okay, so now I do the following 3 remarks, which are these 3 remarks are as follows. So, the first one is that d phi epsilon, so d of phi epsilon to the minus 1 in the point phi of epsilon y is equal to d of phi epsilon to the minus 1 in the point y. That's just a chain rule. Okay. And the second one is that if you expand, actually, yes, this to the minus 1, what you get is that you get the identity minus epsilon, the gradient of x, plus little o of epsilon. And if you expand the determinant of d phi epsilon of y, you get 1 plus epsilon, the trace of the first order term, so it will be the divergence of x, of epsilon. So you plug all of this here, and what you get, yes, you then expand this guy, and yes, what you get is that the integral where u is positive of, so okay, these things is, I mean, the 0 order term should be the energy of u in omega. Yeah, that's. And then I have epsilon, and now let's see if I mess it up with a sign, but I hope not. So the integral where u is positive, and then I have essentially the 2 terms coming from the determinant, which should be once is du square, yeah, it's du square I think so, the divergence of x minus dx du twice. That's important. Yeah. And then I have a little o of epsilon. Okay. So what I get here is, I can do it by hand. Or I'm breaking the okay, let's not do that. So what we get here is that for a minimizer, the first term has to be 0, so larger, sorry. For a minimizer, the integral of, I told you that there is it's my relaxation time, it's very small. The integral of twice dx du minus, maybe I want to write like this, du square divergence of x plus lambda divergence of x has to be 0 for all x which are smooth and compactly supported in omega with values in RT. Okay, so this is what is this is what is coming from the first variation. Okay, it's minus lambda, yes. So now again I'm gonna do something which is, so this is perfectly rigorous at the moment. So I'm gonna do something which is formal, which is actually not really gonna do too much, but sketch it, which is to show, to essentially, so imagine that, this is actually works for any minimizer, so it works for lambda equals 0 as well, right, this computation, and but then you are dealing with harmonic functions. And so somehow this guy is going to be 0, but in a sense, you know, that the Dirichlet energy is convex, so there should be only a optimality condition. So say Laplacian equals 0 should sort of encompass all the optimality condition, because for a convex variational problem you can always have one optimality condition. They are all the same. So these things somehow should vanish in the bulk because of the condition that the Laplacian is 0. So it means that it's a term which, if it goes somewhere, it has to live on the boundary of the sets where I'm integrating. Remember that this is integral, this is where u is positive. Okay, for these two terms doesn't change, but for this it's important. Okay, so essentially this means that you should expect that by suitable integration by part, what is going to happen is that you can push these terms on the boundary. Okay, and this is indeed the case, and you can prove. I'm not going to do it. It's just a careful integration by part that if I do now on the blackboard, it's going to be a disaster. That this is equal to the integral, assuming this set to be reasonably smooth, so that you can actually perform integration by part. This is equal to the integral of du on the boundary of u of du square minus lambda times x dot nu, where nu is the exterior normal. So, and this has to be 0 then. So this means that if lambda is arbitrary, what you expect to have gained as further optimality condition is that du square is equal to lambda on the boundary of u positive, right? But on the boundary of u positive, what would be the normal? The normal is proportional to the, right? So on the boundary of u positive, again, if everything is smooth, you expect the normal to be equal, so the exterior normal to be equal to minus gradient yeah, the exterior normal should be that. Minus gradient of u over gradient of u. So you see that essentially here you are also prescribing a Neumann condition. Okay? So on the boundary of u positive, so the remark here is the following. That's the key remark. That's why in free boundary, if you want, is that on the boundary of u positive, we are prescribing, so, I mean, let's say, let me try it slightly better. So, we expect, so let's say this is not a remark, it's a conclusion, that we expect a smooth solution to solve Laplacian of u equals 0 in u positive. Okay, let's say d nu u equal lambda on the bound, square root of lambda actually, it's okay. On the boundary of, soon lambda will be 1, on the boundary of u positive, and obviously, I mean that's u equals 0 on the boundary of u positive. That's so you see that you expect the solution to solve somehow an overdetermined problem. So, right, you can't prescribe at the same time the Dirichlet and the Neumann data. This implies a lot of rigidity somehow. So this in particular tells you that the problem is not trivial and that the free boundary is a free variable of the problem because it has to accommodate itself in a way that you can prescribe these two things. I mean, it's not that any, right? Because otherwise the problem would be trivial. You say, oh, I give you a set, I prescribe there, Dirichlet and Neumann, and this would be the solution of my Bernoulli problem. So basically any set can be the positivity set of a solution of the Bernoulli problem. You can't do that. You can do it locally if the boundary, if I'm prescribing a set with an analytic boundary. That's Cauchy-Kovalevskaya theorem. But so you see that to solve the free boundary problem, you need somehow, to generically solve it on so let's say to solve it on an arbitrary set, you need that set to be analytic, so not that arbitrary. And in a sense, what is the goal of the regularity theory is a sort of reverse take on Cauchy-Kovalevskaya. Since you have that U is solving this is forcing this set to not be too bad, right? Because on a bad set, you shouldn't be able to do that, okay? So this is telling you that the set where U is positive is an unknown of the problem, which try to accommodate itself in a way that that it's possible to solve the Dirichlet and Neumann problem at the same time. So for instance, for those, okay, here there is one part I'm missing, obviously, and this is all inside of omega. For instance, if omega was Rn, it's a well-known theorem of Serrin that the only way to solve, the only solution to this problem, okay, no, this would be, okay, if you change a bit the right-hand side here, this is forcing the thing to be a ball. For instance, if you put 1 or minus 1, yeah, 1 as a right-hand side. Okay, so this is a globally overdetermined problem are extremely rigid, and locally overdetermined problem, that's a it's usually the case that rigidity for global problems should imply, I mean, it's not imply, but it's related to regularity for locally over-determined problem, right? You can always find locally something like that because, I mean, you prescribe the boundary data and you solve this problem. So can't be too rigid, but still it also can't be random. And going from rigidity to not being random, for instance, means that you expect the free boundary to be smooth or somehow well behaved. Okay, so let's see. Okay, so these are the Euler-Lagrange equation. Maybe I can give you another way to imagine that these are the correct Euler-Lagrange equation by giving you the following exercise. Consider the following 1D. So look to the 1D version of this problem, okay? So find U from, say, 0L to R, so to 0 plus infinity, that minimizes the integral of U prime square plus lambda, the measure where U is positive among all functions, which are, say, 0 in 0 and 1 in L. And essentially, by what I say, this function has to be either 0 or harmonic. Now, there are not a lot of harmonic functions in R. So essentially, what you expect to see is, so if this is 0, this is L, this is 1. What you expect to see is the function to be 0 for some times, and then at some point it has to detach with a slope and be affine. And you see, I mean, obviously, but if you believe to that computation, this slope should be square root of lambda, but you can also do it by variationally showing that it's the best combination, okay? So you see where, I mean, the slope depends on the point where you, there's only, it's fine, very fine. It's a one-dimensional problem, right? You only have this to decide where this point is, and if you compute it, you're gonna see that it's such that this slope should be lambda. I mean, x minus whatever, okay? And you also see the link with the capillarity question here, because in a sense, this is a sort of relaxed version of I mean, relaxed, simplified version of the capillarity problem. Okay. So this is for the Euler-Lagrange equation and a bit of the intuition behind why I might want to expect regularity. So let's move to discuss regularity. So actually, okay, first say, so regularity. And again, regularity splits into two things. One is regularity of U, which maybe we don't care, but in a sense is instrumental to understand the other part, so we should care. Of U, and the second one is regularity of U positive. Okay, so these are the two main tools. And regularity of U, you see from this picture that you cannot expect any better than Lipschitz. right? Because this is a Lipschitz function and you do not expect anything better than that. And in a sense, so regularity of U, so by the 1D example, we cannot expect better than Lipschitz. Actually, when you study regularity, and this is still linked, I mean, regularity is also related, I mean, the optimal regularity of the problem is also related to its scaling. That's a general fact, because, I mean, the point that a variational problem has no preferred point, neither preferred scale, is something that can be used a lot in regularity, right? All points and scales are the same, so because, I mean, you only look for I mean, in a sense, the class of minimizer, I mean, if the class of minimizer is invariant by some translation and scaling, this is giving you a lot of information. So what would be the scaling which leaves invariant this problem, which at this point I raised? Okay, so what would be the scaling that leaves invariant this problem? Okay, you can try to guess, but the other way to guess it is via dimensional analysis. So maybe show you this trick, so which probably most of you knows. So what are the dimensions of this term? The dimension of this term are the dimension of U divided by L. So this is the gradient square times L to the D, right? And the dimension of this term is L to the D. So these things are the same if the dimension of U are like a length, right? So this suggests that so this suggests that if U is a minimizer, in omega, then U x0 r, which is U of x0 plus divided by r, is a minimizer in omega minus x0 over r. Right? And indeed it's the case. I mean, this can be checked by computation, okay? So this say also that any type of estimate I can do should be invariant by the scaling. It should be something which only depends on the problem and not, and it also tells you that actually you can use this scaling to get a lot of estimates, which a priori maybe you get, if you get some estimates, you can apply the scaling, and this estimate somehow becomes better, okay? So, and this also tells you, you see this is actually the scaling which preserves Lipschitz continuity. So it says that Lipschitz continuity seems to be optimal. Not only that, it says that if you can show Lipschitz continuity, and you pick x0 in the free boundary, this family here, right? So why, maybe this is also a good point to say why I care about the optimal regularity for U. So if we know that U is Lipschitz continuous, that if we know that U is, say, universally, well, let's say Lipschitz continuous, and x0 is a point on the boundary of U positive, then the family U x0 R, which is precompact in the uniform topology. But then now this means that, so what is, how does it look, the free boundary for this family? So if this was your U was positive here and you're picking a point x0 here, essentially if you take a ball centered on this point, it's U of x0r would be defined in the ball of radius 1, right? So this would be B10, and the free boundary here will be a zoomed version of the free boundary of U. So this means that this family is sort of capturing the infinitesimal behavior of your function and around the free boundary, and being precompact, in a sense, it tells you that at least there are limiting behavior for this for the. I mean, there is. That doesn't tell you that there is a limit behavior. That would be too much, but that you can try to use these ones to analyze what is happening infinitesimally around the point. Okay. Point is that this is precompact, but it might have a lot of limiting points, of different limiting points. Okay, and part of the regularity theory to show that this doesn't happen too often. Okay, but that's to convince you that Lipschitz continuity is key, and I'm not sure. I mean, I'm pretty sure I cannot prove Lipschitz continuity, but maybe I'll prepare an estimate in this 10 minutes that will be instrumental for several things. So let me go. Okay, maybe let me do this. Okay, let me conclude with, no, this is up. So let me conclude with final estimate. Which number are you? This? Okay. Okay, so say harmonic replacement. So I mean, except that giving you the 1D example, I didn't convince you that U doesn't want to be harmonic, right? It's minimized in two terms. Maybe you just say, okay, the harmonic function minimizes one. Maybe they would also minimize the other. Well, they don't, right? Because since the function is positive, I mean, I'm always looking to positive, say, non-negative functions. Harmonic non-negative functions are strictly positive because of the minimum principle. So the measure where U is positive is huge, is everything, right? So there is the balance that the function, as my 1D example was showing, there is a balance that the function would like to, I mean, balance where it's harmonic, where it is zero. So in particular, you expect that the set where U is zero sort of control the distance between U and an harmonic function, right? Because if U is not zero, it has to be harmonic. right? And this is actually the following, these estimates. So let's call it lemma. I'm gonna use it. Let U be a minimizer. BR x0 containing omega, and V x0R be the solution of delta V x0 0 in B x0R and equal U on the boundary. So I'm taking the harmonic replacement. So in any ball, I take a ball and I look to the harmonic function which has the same boundary value of U in that ball. Okay? Then the integral of the ball of d du square minus dv x0r, I mean, square is actually equal to the difference of energies. Correct? Which is less or equal, measure where U is equal to 0 in the ball. Okay? And maybe here there is a factor, I think it's correct. Okay, so you see that the measure where U is equal to 0, it controls how far the function is from the harmonic. Okay? And this is in particular, if you want, less or equal than R to the D. So, yeah, before I sketch the proof, which is immediate, let me just give you a corollary. Which I'm not proof, just a PDE. So U is continuous. So it's just continuous, not Lipschitz continuous. It's just a qualitative thing. Okay? And actually the proof is the following. Indeed, any functions such that for all ball 0, where this is the harmonic replacement, and this is a square, is of class C alpha lock for all alpha less than 1. Okay? So this is a sort of PDE effect, I mean like variation slash PDE effect, which is related to Murray spaces. Well, that's a way to prove it. I mean, there are several. And it's not really, I mean, it's interesting by itself, but it's not too much related to the problem. And just say that already this is giving you some, so here it's a constant. Already, I mean, for a uniform constant, C. C shouldn't depend on the ball. This is effect about regularity of functions, so, and then Murray estimates. So I'm not going to prove it. I mean, if you're interested, I can give you some pointers. But you see that this is not giving you the optimal regularity, right? You're missing the final alpha. But at least I can assume U to be continuous safely. I mean, Okay, so maybe, okay. So just maybe if you give me 1 sec, I'll show you how to prove this inequality, and then I finish, sorry. I mean, the second one is obvious, right? Because it's coming down. The only thing is the equality. The second inequality is just, so the actual inequality is just because of comparison of the energy, right? And effects. Right? And also the first one is not hard. So proof. So the inequality is just that the energy of U in BR should be less than the energy of V x0R in BR, and that the measure where V, let's say, 0R is positive is, I mean, this set actually is BR, right? Because V is harmonic. So that's is giving you the inequality, and to prove the equality, so the first equality, you just observe that, let's see, du square, so basically that's a pointwise equality, which is du square is equal to du square minus dv square minus twice right? That's the pointwise things about vectors. This one? No, it's with the minus. I need it with the minus. It's the convexity of the square. I mean, it's. I mean, this is an equality, I think. Okay. Because you have twice of it, right? Here. So it's plus. Now you integrate this, right, on the ball, and this is 0. Because U is harmonic, so by integration by pairs. Right, because this is equal to the Laplacian of V, maybe without the sign, times U minus V. And there is no boundary term because these are equal on the boundary. Okay? So that's a way to say that harmonic, I mean, it's a quantifying how much harmonic function are minimizer for the Dirichlet. Okay? So it's just a trivial fact. Okay. So I think I'm done, right? Yeah.